Thank you, everyone, for coming today. We're having the second of our webinars this year. This one is on modern ball screws, the advantages of internal returns. Our primary presenter will be Bruce Gretz, the National Key Account Manager for Steinmeyer. Also joining us in the Q&A portion will be George Jaffe, Executive Vice President of Steinmeyer, and he'll be answering your questions as they come in later. So with that, Bruce, please take it away.
Thank you very much, and I appreciate everyone joining us today, this afternoon. We've got a lot to talk about, fundamentally about the Steinmeyer design philosophy in ball screw returns. And fundamentally, our philosophy oriented around internal returns. We'll talk about some history, and then our design philosophy and our product line that derives from that. We'll talk about the limitations of tube returns. We believe there are some very fundamental limitations there that really cap their performance. We'll get into some particulars about the Steinmeyer design philosophy. And as you see here, a list of really 6 major return types that fill out the Steinmeyer product line. They're all driven by that philosophy. And then we'll wrap up with some conclusions and hopefully answer your questions. So let's get started. And I always like to start with a bit of history. I think it helps to understand where you've been, to understand where you are right now. Commercial ball screws really originated back in the 50s. And you see right here one of the original tube-style returns. This was from a Saginaw steering gear. If you got an old Ford Fairlane or maybe a Chevy Corvette or another such car, it's very likely to have this component inside. And as you see very clearly here, it features dual tube returns. Very easy to fabricate and easy to assemble. And that's really how ball screws were first commercialized. And it's very easy to see why that choice was made. You bore holes in the nut body, bend a tube, insert the tube and clip it in, and you're done. So it's a very natural type of design very early on. Of course, tube returns have evolved, as you would expect, over the years. Here's a picture below of a relatively modern tube return, and a schematic on the right side. But fundamentally, the same limitations and design parameters apply here. You've got a tube jutting outside of the outer diameter of the nut body, and as you can see, this requires a 90-degree deflection at both ends of the tube. End of the tube here, and when they leave the tube at the opposite end, being applied back on to the track. So those deflections are very extreme. And as a result of that, the fundamental design philosophy, the tube returns have quite a few specific limitations. This kind of direction change causes higher frictional losses, which generates more heat, and also creates higher variations in friction torque. There's also, of course, a higher risk of ball jamming, and we'll talk about the speed rating throughout the day as well. The DN value is limited to about 70,000, and that's computed as the maximum rotational speed in RPM multiplied by the shaft diameter in millimeters. So for tube returns, you're really limited to about 70,000. There's also a larger outer diameter required for the nut as a result of the tubes. So size and spacing can be challenging. Also, some type of a design feature in the tube is required to guide the ball back onto the track, either a pin or some type of a scoop, and those are often very small features which are subject to failure. And we've seen a lot of pin failures out in the field in tube returns, and it's a really significant design limitation of tubes. Also, there's a lubricant leak possibility. That borehole and tube is difficult to seal, and so you'll frequently see lubrication losses through the nut body. And then finally, tubes are generally incompatible with rotating nuts because of the asymmetrical radial forces as a result of the tubes. When a nut starts to rotate, it can cause some problems at any type of a speed. Now, Steinmeyer uses internal returns, and they're not simple to design. We have a very long history in development there, and there's a lot of complexity involved in internal returns, so it's not an easy solution. And as you'll see in the designs that we discussed today, a lot of complex shapes among our deflectors. They're certainly more difficult to design and manufacture, and historically, internal returns have lagged the market compared to tubes. So we're sticking by our design philosophy of using the tangential deflection, following the natural trajectory of the ball, and thereby minimizing the deflection forces. And what we've done is to really apply modern design and manufacturing techniques to close the performance and manufacturing gap with tubes. Of course, we're using CAD. We're performing precision machining of deflectors, which is rare in the industry. As I said, you'll see a very wide variety of deflector designs. And the end result here is higher speed than the DN value of the nuts, higher efficiency, lower heat generation, and significantly higher reliability. And those are very, very important, of course, for almost any application. For industrial applications where servo control and precision servo control is required, that lower torque variation throughout the nut travel is also extremely important. So for all these reasons, Steinmeyer has never used and will never use a tube return. So let's get on to our design categories, and we'll delve into some detail on each of these. The first is the track-to-track return, and this is really our first return design, and still the workhorse of the product line. As you can see in the schematic, the deflectors are removed and there are bore holes visible in the nut body, and they're labeled here also. And so you can see inside the nut travel and the ball travel, and the deflectors simply guide the ball onto the next track, lift it up and drop it onto the next track. So each deflector serves one ball circuit. It's a very easy motion of the ball. Also, the deflectors are sealed into the bore holes with an epoxy. And as you can see here too, they're flush to the outer body of the nut. So there's no external dimension on the nut body. And a lubricant is impossible to leak out because of that epoxy seal. This design, the track-to-track return, is available on a very wide range of shaft diameters and nut types. As I said, it's really the workhorse of our product line. It's particularly preferable for small balls and for small lead diameter ratios, typically less than 0.5. The speed rating achieves 120,000. So it's a very significant increase from the 70,000 limitation of tubes, and for that reason is the widest and most popular choice today. The variation on the internal track-to-track is the liner return. As you can see, there's a liner piece that's inside the nut body, the blue piece here, and it's really multiple deflectors integrated into one piece. So you have a single component construction, and it's completely inside the nut. In fact, there are no bore holes required at all in this design. We developed this originally for the aerospace industry. It's got a very high load capacity and a short nut. You can see a great number of deflectors spaced close together inside the nut body for a very high, very dense load capacity. The single piece design of the deflectors makes assembly and reliability very easy, and it's also inherently fail-safe. If the liner fails, the ball will not fall out of the nut. They will lock in place, but they will not catastrophically fail, and that's critically important for aerospace applications. Next is the ultra-speed return, and this is really our first through-the-nut return design. You can see the balls in the schematic here returning through the nut body, and actually two return paths here because there are two separate ball circuits for this dual start threaded design. As a result, there's pairs of deflectors at each end of the nut body. Typically, it's designed with dual start threads, and you can see the multitude of balls and return paths in this short nut body also gives a very high load capacity for the length of the nut. In the photograph below, in fact, you see the ends of the deflectors, the black pieces are the ends of the deflectors. So again, they are arranged in axial pairs. This is designed, of course, for high-speed operation. For large leads, where we're talking about a lead diameter ratio greater than 0.5, the track-to-track deflector does not work as efficiently on such large leads, and so that this through-the-nut design is preferred. And in fact, it can reach the even higher speed rating with a DN up to 160,000 and a linear speed of about 1.5 meters per second. Another through-the-nut return we call the end cap return. Again, whole board through the nut body for the return path. And this time we have plastic caps at each end as the nut serve as the deflectors. And that extra length there can also accommodate our combination wipers, which, as you may know, consist of a ring of plastic fingers as well as a felt nut ring, and that all fits inside the length of the end cap, so no additional nut body length is required here. And these plastic end caps, of course, lower the weight, but also very significantly reduce noise by up to 50%. So many of you have used ball screws or heard them, can often be quite noisy. This noise reduction is welcome in many applications. The end cap returns are really designed for relatively small shaft diameters from about 5 to 20 millimeters. But they can still achieve high speed, and you see here again the dual start design, which can support a linear speed of up to 2 meters per second. One of our newer designs is the Z deflector, and you see it here pictured with the deflector next to the nut schematic. This is our first all-plastic return system. In the end cap, previously we had plastic deflectors. Here we have not only plastic deflectors, but the entire return path inside one integrated plastic piece, which of course fits onto the nut body as shown here. This is primarily designed for shafts with solid bearing shoulders on both ends, and in that case it's impossible to assemble the nut onto the body with the balls. Here you have to assemble the nut and then assemble the ball as a second step, and then fix the deflector, and you're done. So this design accommodates that approach. We also have the ultra thrust return, and this is another utilization of a plastic return system. And here you see multiple plastic returns end to end to accommodate a very large number of balls and very high load capacity. Now the ultra thrust line has been around for a few years, and if you've heard about it from Steinmeyer, you'll know that we originally employed the track-to-track return system for ultra thrust. We achieved the higher load rating there with large balls, starting with 15 millimeter ball sizes and eventually accommodating 19 millimeter ball sizes, still using the track-to-track return. This new ultra thrust 9 series return that you see here is the newest product in our series, and the 9 series refers to the plastic deflectors that you see here, either 2 or 3 end-to-end to accommodate a very large number of balls and extremely high load capacity, still in a fairly short nut. And this again is accommodating balls up to 19 millimeters. And for the maximum sizes here, we can actually achieve a dynamic load capacity of 1,400 kilonewtons, which is about 140 tons. So that's really the highest extent that we've gone to date. And the main application there naturally is replacing hydraulics and supporting the use of electromechanical actuators in their place, which are naturally more efficient, more environmentally friendly, and it's a growing demand from our customers, and the ultra thrust line is reaching a very, very high load capacity to support that. So in conclusion, I hope I've explained to you why we believe that internal returns are clearly superior to tubes. That's our fundamental design philosophy, and it all revolves around tangential deflection, and that's going to deliver higher speed, higher efficiency, and higher reliability across the product line. Without any tube connection on the nut, there's no loss of lubrication. That's another very significant advantage in many applications. And what we've done at Steinmeyer is to bring together modern design and manufacturing methods to allow internal returns to achieve very widespread adoption without any kind of a cost penalty, but delivering very clearly higher and clearly more desirable performance across the product line. I appreciate your attention, and I'd be happy to take any questions that you have.
As we just noted in the chat, if you have questions, that we'd be happy to answer them during the Q&A session. And somebody was quick to jump on that right away. How prone to failure are the plastic track-to-track return inserts?
Well, they're very reliable and very stable. Of course, we have an enormous amount of field experience with that. I should add that we produce the track-to-track deflectors in both metal and plastic. Our field experience with those is very deep, and they are extremely reliable. And keep in mind, with the track-to-track, we have really minimal forces on the deflectors because it's just lifting the ball to the next track. The angle of deflection is very small, and the loads on the deflectors are consequently very small as well. So we have a great amount of confidence in their reliability.
Bruce, there was a similar question asked beforehand. Is what type of plastic, what are the materials that the deflectors are made out of?
I'm not sure the exact material, and of course you can imagine some of the information is going to be proprietary. I will say that if you have the chance to visit the Steinmeyer factory, I would encourage and invite anyone to do so. You'll see an enormous amount of attention paid to deflector fabrication, and that's one of the uniquenesses and strengths we have in the marketplace. Just as some are metal, and the predominant plastic material that we're using is probably a form of PEEK.
Bruce, another question about noise difference in the metal versus the plastic inserts.
They're probably similar in terms of noise generation. Of course, that depends on a lot of factors in terms of the size of the screw, the duty cycle of the application. George, would you care to comment on the noise?
Well, you know, plastic tends to be quieter, but you know, in rough terms, it's not. I mean, it can be several decibels, you know, quieter, but usually it's not an issue.
There was a question asked before the webinar about the noise with tubes. Is that really a problem with them, or is it just simply they're just noisy?
Well, you know, tubes are notoriously noisy, and the higher speed you try to run them, the larger the screw, the higher the noise. And so we've had many customers flagging that as an application problem, and with the end cap design, you see we've really tried to address that head on. So we're well aware of it, and the reason is that the marketplace has been asking for it very strongly.
Bruce, we have a few more questions that are coming in, and thank you all for sending them. Can you discuss your wiper seal technology? This particular person is in aerospace and is concerned about water entering the crossover and freezing, forcing the balls down the screw, resulting in damaged screws and ultimately screw failure. So maybe an aerospace discussion about how wiper seal technology can be combined with this.
Well, generally speaking, we have a wide variety of wiper designs. You know, for the industrial world itself, we've designed several different wiper types, and we've been very innovative there. And aerospace, as you know, that's a continuing concern. We actually have a very innovative icebreaker design that we have implemented recently for aerospace. So we're quite active and innovative in wiper design.
The next question, Bruce, is the nuts are usually coupled together to counteract moments and movements and forces. Why does the high thrust line have 3 instead of 4 ball lines? I believe it's 2.
Well, we have, yeah, that's our newest product line, and it's currently configured with either 2 or 3 return circuits, and potentially that could be extended. But as you saw, the 3-circuit design is already reaching 140 tons in load capacity, so that's very, very high and capable of replacing hydraulics in quite a few applications.
Another question that came in advance, Bruce, and again, if anyone out there has questions, we're more than happy to have Bruce address them, so please use the chat feature. Are internal returns more or less susceptible to damage if the ball, nut, and screw are misaligned?
Misalignment is an ongoing concern and out in the field and a lot of industrial applications in particular, and you get into high speed, high dynamic load conditions, and some screws can be very sensitive to that. The tubes are notoriously more sensitive to misalignment, so that's one of the additional advantages of internal returns. And it all gets down to the forces applied to the deflectors, and we are a little more forgiving on misalignment.
The reason why tubes are considered somewhat more susceptible is because with tubes you're pushing a lot more balls in the path, and that's the main reason. With the individual deflectors, you're only dealing with 2 or 3 balls.
All right, last call for any questions for Bruce, and then the topic of internal returns. Excellent. Well, if there are any questions out there that you'd like to ask directly, Bruce's email is on screen. Feel free to reach out by email. Otherwise, thank you so much for attending, and we look forward to seeing you again in the future.